Hi, I'm Aditya, and for my Chem Summative, I'm going to explain the manufacture of ammonia. The topics that we're going to be covering are explanation of ammonia, the molecular shape, effect of catalyst, high pressure, high temperature, and redox reaction. I'm going to start with the explanation of ammonia. Ammonia is a compound of nitrogen and hydrogen. It is a colorless gas with a characteristic pungent odor. Ammonia contributes significantly to the needs of terrestrial organisms by serving as a precursor to food and fertilizers. The most common ways in today's society to manufacture ammonia is the Haber-Bosch process, which we will talk about later. It is composed of nitrogen and hydrogen, which covalently bond together. The nitrogen atom in the molecule has a lone electron pair, which makes ammonia a base, or a proton acceptor. One of the most important characteristic properties of ammonia is its basicity. Ammonia is moderately basic. A 1.0 mole aqueous solution has a pH of 11.6, and if a strong acid is added to such solution until the solution is neutral, 99.4% of the ammonia molecules are protonated.
And now I'm going to talk about the molecular shape of ammonia. In this molecule, the center atom is nitrogen, which is bonded with three hydrogen atoms. When there are one lone pair and three bond pairs around the central atom, there are two types of repulsions: lone pair bond pair and bond pair bond pair. Since the lone pair bond pair repulsions are greater than bond pair repulsions, the bond angle between the bond pairs in ammonia is reduced from 109.5 degree to 107.3 degree. When drawing the shape of trigonal pyramidal molecule without lone pair, you can see that the three bond pair form the shape of pyramid with a triangular base, and that is why a molecule of ammonia can qualify as trigonal pyramid.
Next thing I'm going to talk about is how ammonia is produced in factories with special significance of the Haber-Bosch process. In factories, first hydrogen is obtained from air and purified of sulfur. Next, using steam reforming and water gas shift reaction, hydrogen is obtained. It's obtained out of these following reactions. In the first reaction, methane reacts with water to form carbon monoxide and hydrogen. And the second one, carbon monoxide reacts with water to form carbon dioxide and hydrogen. After this, to produce the desired end product ammonia, the hydrogen is reacted with nitrogen, which is derived from air. Using a magnetite catalyst, this is used to form anhydrous ammonia. This last step is known as the ammonia synthesis loop, also can be referred to as the Haber.
In the reaction of nitrogen with hydrogen, the hydrogen atoms lose electrons and undergo oxidation. In other words, the hydrogen atoms are oxidized. The nitrogen gains electrons and undergoes reduction. In other words, the hydrogens are reduced. Because oxidation and reduction both occur in this reaction, it is known as an oxidation-reduction reaction or redox reaction.
Bosch process. Now I'm going to talk about catalysts. A catalyst is a substance which speeds up a reaction, but it is chemically unchanged at the end of the reaction. When the reaction has finished, you would have exactly the same mass of catalyst as you had in the beginning. In this case, the catalyst is magnetite. It is a ferromagnetic mineral with the chemical formula of Fe3O4. While we're talking about catalysts, the activation energy is also important. Collisions only result in a reaction if the particles collide with a certain minimum energy called the activation energy for the reaction. You can mark the position of activation energy in a Maxwell-Boltzmann distribution to get a diagram. For example, like this one. In this diagram, the y-axis represents the number of particles and the x-axis represents the energy. As you can see in the graph, the blue part represents the number of particles which do not have enough energy to react. The green represents the particles which have as you can see, the green part of the graph is much less compared to the blue. Only the particles represented by the area to the right of the activation energy will react when they collide. The great majority, as you can see, do not have energy and simply will bounce apart. Catalyst and activation energy. These are important because to increase the rate of a reaction, you need to increase the number of successful collisions. One possible way of doing this is to provide an alternative way for the reaction to happen, which is a lower activation energy. This is exactly what the catalyst does. In other words, to move the activation energy on a graph like this, adding a catalyst has exactly the same effect. The number of particles again on the y-axis and the energy on the x-axis, as you can see. The particles which don't have enough energy to react is the blue, and the particles which do have enough energy to react is the yellow and the green. The yellow part is the extra particles which have enough energy to react because of the catalyst, and the green is the original particles which would have reacted anyway. A catalyst provides an alternative route for a reaction. This alternative route has lower activation energy, thus making it easier to react. This can be shown on an energy profile like this, where energy is on the y-axis and progress of reaction on the x-axis. As you can see, the blue line or curve is the activation energy without the catalyst, which is much higher than the red, which is the use of catalyst. Next, I'm going to talk about how temperature affects the manufacture of ammonia. As you increase temperature, the rate of reaction increases. As a rough approximation for many reactions which happens at around room temperature, the rate of reaction doubles every 10 seconds. This is not to be taken too literally though, as also in case of ammonia. The particles can only react when they collide. If we heat a substance, the particles move faster and so collide more frequently. This speeds up the rate of reaction. Again, the activation energy is important in this case. As the minimum, because of the kinetic energy of the particles, the minimum energy required is less. We can mark the position of activation energy again on a Maxwell-Boltzmann distribution to get a diagram like this, which is almost exactly the same as the one before. There are two opposing considerations when we are looking at the Haber-Bosch synthesis process. The position of the equilibrium and the rate of reaction at room temperature. The reaction is slow and the obvious solution is to raise the temperature. This may increase the rate of reaction, but since the reaction is exothermic, it also has the effect, according to Le Chateau's principle, of favoring the reverse reaction and thus reducing the amount of product given by this equation. As the temperature increases, the equilibrium is shifted and hence the amount of product drops dramatically, according to the Van Hoff equation. Thus, we can say or suppose that a low temperature is to be used and some other means to increase rate. However, the catalyst itself requires a temperature of at least 400 degrees Celsius to be efficient. Therefore, pressure is the obvious choice to favor the forward reaction.
The next thing I am going to talk about is the use and effect of high pressure in producing ammonia. In order to understand this, we need to understand the Lichat principle. A French chemist, Henri Lichat, in 1888 summarized his work on change to equilibrium systems in a journal statement called Lichat principle. It states that a dynamic equilibrium tends to respond so as to relieve the effect of any change in this condition that affect the equilibrium. In this case, when the volume of a mixture of gases decreases, the pressure of the gases must increase. Lichat's principle predicts a shift in the equilibrium to relieve this change. Therefore, the shift must tend to reduce the temperature of the gas. Molecules striking the walls of container cause gas pressure, so as a reduction in gas pressure reducing in gas pressure at constant temperature must mean fewer gas molecules. Contain Consider the following reaction again. In this case, the less number of molecules formed in the product side, which is ammonia.
And that concludes our presentation. Thank you for listening.